Howdy there. My name is Joshua Kwa.
I'm Adrib, dude.
Howdy, my name is Daniel Olaja.
And we're here to talk about Merkle trees. Now, before we get started on Merkle trees, we need to understand exactly what hashing is. Hashing is the process of converting a string or an input key into a different value. This value, called a hash value, is produced through a mathematical function that is usually a one-way conversion, meaning that once it's turned into the value, it can't be turned back into the string or the input key. Hashes are unique for each input key within a data structure. A representation of this is seen over here to the left, where you have the different input keys or strings put into the mathematical function, which is the green block here, and then coming out as the hash value on the right. Now that we understand hashing, we can look at what Merkle trees are. Merkle trees were invented by Ralph Merkle in 1979, and they're also known as hash trees. This is because each node is the hash of the concatenation of its children nodes below it. Each non-leaf node is representative of its children's nodes, and Merkle trees are most often implemented in a binary tree format, which can be seen off here to the right. As you can see in this tree, we have data of A, data B, data C, and data D represented in the bottom nodes. As you move up the tree, you can see the next the parent node of it is hash of A, hash of B, hash of C, and hash of D. Once you get into parent nodes that have two children, such as H of AB, you can see that H of AB is comprised of the hash of A plus the hash of B, all of which is hashed together again to form H of AB. This continues all the way to the top node, which is called the root node, and is representative of the entire Merkle tree. Some of the advantages of Merkle trees are that they can be used to distribute parts of data across multiple systems. This is useful for both data storage and security. This structure allows for large data mapping at speed and for any changes within the data to be identified with ease.
Hi, this is Adrib, and now I'm going to talk about the applications of Merkle trees. Merkle trees are used in distributed systems for efficient data verification. And the reason I say efficient is because Merkle trees uses hashes instead of full files. And hashes are encodings, and they're lightweight, and they consume much less memory than full files itself. Merkle trees can also be seen in systems such as blockchains, which are commonly used for cryptocurrency transactions and validation. An example of cryptocurrency would be a Bitcoin. Merkle trees are also used in Git version control to track changes in files, because Merkle trees have the ability to detect any change in content in its leaves. And the reason it can do that, because Merkle trees are constructed using hash functions. When there is a change in leaves, the hash function itself changes. Merkle trees are used in NoSQL systems to detect inconsistencies between replicas of entire databases, which is a great security feature because you know if your database is corrupted or not. So why do we use Merkle trees? Merkle trees use hash functions, and therefore it can track any changes made to the leaves and update the ancestors accordingly, like I explained on my previous slide. Merkle trees are lightweight since it uses hash functions, which produces hash encodings, which take up much less memory in your computer. Merkle trees have logarithmic runtime performances for search, delete, and insert functions, which are three essential functions for any data structure. And a logarithmic runtime performance, as we know, is always great. Merkle trees are mostly used in applications that require data consistency, verification, and synchronization, like I've explained in my previous slides. So now we have a table of the time complexity of Merkle trees. As you can see, the worst time complexity for search, insertion, and deletion operation is logarithmic, which is great, and that is a great sign for any data structure. The traversal operation is linear time instead of exponential time. So that, I believe, is also a great stat for any data structure.
Daniel?
Okay, so now I'm going to talk about some important functions and operations of the Merkle tree. One of the functions is insert, which is used to populate the Merkle tree. The contents of each node are hashed and added to the tree. After this, a parent node is created, and the hash codes from the children are combined and hashed to generate the hash code of the parent. These steps are repeated until we reach the root, At the end, the Merkle tree is fully populated, and any changes to the contents of the children will propagate throughout the Merkle tree. The next operation I will talk about is the comparison. The objective of the comparison is to verify that the contents have not changed. And if the contents of the tree have changed, you should be able to find the file that changed. We begin by comparing the hash code of the root in both trees. If they are different, then the content of one of the leaves have changed. We then start to check the hash codes of the children. We check the hash codes of each of the children from left to right. If the hash is equal on one of the children, we then move to the sibling node. Next, we compare the siblings, and if the hash code is different, then we compare the children of the sibling, and we repeat the process recursively. Eventually, by checking the hash codes of each of the nodes, we will reach the leaves, and we will be able to spot files or data that changed.
Okay, and these are some of the sources that we used to make this. I hope you learned something about Merkle trees, and thank you for your time. Have a good day.
Thank you.
Thank you.